Hi there, join me once again in this video where I am going to talk about reactions involving benzene and benzene derivatives. Now we have discussed that the aromatic compounds are stable to an extent that they don't really undergo a lot of reactions that we have experienced before in the other chapters. So the question is, what kind of reactions do they undergo? Okay. We looked at a reduction being done to achieve a cyclohexane under harsh conditions, like 100 atmosphere pressure and 150 degrees C will be able to do that transformation, though the reaction is slow. Okay. Another reaction we could do is to selectively reduce the styrene such that the benzene ring is not affected. Okay, so that can be done at room temperature with 2 atmosphere pressure. Another interesting reduction is what we call the batch reduction. So this one involves a radical mechanism step. So it requires the use of an alcohol in the presence of sodium to act as a source of electron, and then with ammonia liquid. So the sodium is able to donate an electron, and that electron we can use fish hook arrows. So that electron goes here, and then we can homolytically cleave this pi bond. And then we end up forming a minus charge on this position. Okay, so it cleaves that. The other one also moves here. So we form a double bond here, and then we end up with the electron in this position. Now, if you look at that, the electron in this position it's going to be stabilized because it is in the allelic position of these two double bonds. Okay, so once we form this negative charge where we have those lone pairs of electrons, it ends up picking a proton. So this is a proton transfer mechanism, and it installs a proton there. The same process is repeated. Sodium donates another proton and creates a negative charge here, which does a proton transfer, and we end up with the batch reduction product. If there are substituents on the ring, then the reaction becomes regioselective. So for example, if there is an electron donating group would actually prefer to have this position to be electron deficient. Okay, so if you try to put a minus charge here, it's not going to be happy. So this position is not going to be reduced. Instead, the position that's going to be reduced is here and here. Okay, if we do have an electron withdrawing group though, electron withdrawing group would actually be happy to have the electrons in this region. So then, if there is an electron in that position, like here, create a minus charge here, then it can stabilize it by resonance. Okay, so therefore, this position is going to be reduced if we do have an electron withdrawing group. Okay, and that's why you see this position has been reduced, and we end up with a product that looks like that. So when you have an electron donating group, you need to be able to predict the product that is being formed, and of course you understand why now. If we have an electron withdrawing group, then we know the position next to the electron withdrawing group is going to be reduced. What other reactions can we do with aromatic compounds? Well, not so much unless we have what is called a benzylic position. Okay, so look at this compound, no reaction, just like an alkane. If we don't have a benzylic position, no reaction. But the moment we introduce a proton in the benzylic position, so as long as there's a proton in the benzylic position, then the reaction would happen. Okay, so here we have a proton So we can oxidize that to carboxylic acid. We can use chromic acid, or we can do this under basic conditions to get the product. Then we do a workup with an acid to form the benzoic acid. Okay. So in other words, as long as we have a benzylic position, we can be able to use N-bromosuccinimide to introduce a bromine there, or we can be able to again use even NBS to introduce a bromine over here in this compound. So as long as we have a benzylic position, we can now kind of begin to do a lot of reactions. The moment we create a halide, then now we can do SN1, SN2 reactions, a lot of other reactions. Okay, so with that we can transform this into an alcohol. Okay, once we transform it into an alcohol, then think of all those alcohol reactions that we learned. We can be able to transform this again into into a halide. Then with the halide group, this can undergo SN1. So here, if we just use water, then we transform it into a tertiary alcohol. With tertiary alcohol again, we can be able to do a variety of reactions. And we can actually be able to transform this into an alkene, where we can just simply do an elimination after transforming the alcohol into a good leaving group. Then we can use can do E1 elimination. We can use a weak base like say ethanol to be able to transform it into an alkene. And then with an alkene again, it opens an avenue for a lot of other reactions. So as long as we do have a benzylic position, then we are good. Thank you for watching, and have a good day.